Hi, everyone. Let me start by saying thank you very much for joining us today. Really appreciate your time wherever you are in the world. I'm really excited today because we're going to talk about some of the latest research here at Fathom and principally about our latest terrain data set, FathomDEM. And hopefully you would have seen that this is a paper that's been published recently. And it is indeed a really exciting next advance really in our work processing terrain data sets. So next slide, please. So I'm joined today by my colleague, Chris Lucas, who really is the person at Fathom who understands machine learning correctly and has really undertaken some superb work since joining us last year. A big thanks also to Pete, who's another developer here at Fathom, who spent a lot of his time processing terrain data sets. And next slide, please. I have the kind of easy job today, which is to just introduce this work. I kind of want to set the scene a bit and talk about some of the history of terrain data sets and principally the work processing them here at Fathom. But it's really going to be down to Chris to talk you through the real substance here. So what are terrain data sets? What is FathomDEM? How have we built this thing? And I'll come back at the end to talk about the various ways in which these data are being used in the real world. And then we'll have a Q&A as well. So please, as we go along, do pop your questions into the Q&A box. There'll also be a quick poll at the end as well. Next slide, please. So I'll start with a question, and that is, why do we need global DEMs or terrain models? So DEM, I'm sure you all know, is a digital elevation model. So why do we need these data sets? Well, we need them for lots of reasons, but principally in my world, we need them to build good flood models. Flood models, as complex as they can be, and you need lots of complex input parameters like river channels and river flows and rainfall. But actually, if you don't have a good terrain data set, the flood model will be useless. The terrain data sets are really the number one thing governing the quality of a model. After all, water flows downhill, and if you don't know where downhill is, then your flood model is not going to be very good. And what we have at the moment on your screen is a flood event that occurred in 2011, and it was a so-called unmodeled loss. What that means is, from an insurer's perspective, is that nobody saw it coming. And the reason that nobody saw this coming is because we couldn't build flood models in this part of the world at the time. Actually, we couldn't build flood models for the majority of the planet. And the reason for that is that we didn't have, or one of the reasons for that is that we did not have good terrain data sets available in this part of the world. And this is what we would call a market failure. This was really us as, I'll sound grandiose, but us as humanity not really understanding the risks here. Next slide, please. So that's why we formed Fathom. We formed Fathom off the back of that flood event. And we formed Fathom because we wanted to try and build flood models covering the whole planet. And we are indeed now doing that. We're building models that cover everywhere on Earth. And in doing that, we've also emerged as the scientific leaders in the space of processing terrain data sets. Because we as a community, and the community here being flood modelers, stand to gain so much from processing these terrain data sets and getting maximum value out of them, we've spent a lot of our time trying to build them. Next slide, please. And I wanted to take you back to the beginning of Fathom and when we started to try and build models in this part of the world. And this is somewhere near to the image I just shown you. So this is the Mekong Delta in Thailand or in Southeast Asia. And what you can see here is a terrain data set that was made available via the US government. So this is a NASA data set called SRTM, or the Shuttle Radar Topography Mission. And what you can see here is that in its raw form, it's actually riddled with errors. So not only do you capture the tops of trees and the tops of buildings, so those areas will look like hills, there's also a whole bunch of instrumentation error here. And that's what these stripes are that you can see. It kind of looks a bit like a zebra. And that's where the aircraft itself pitched and rolled in space. So you had this whole kind of mixture of error sources contributing to give you a very noisy, unreliable, inaccurate terrain model. Fathom, and even the precursor to Fathom in our days at the university, we spent years processing these terrain data sets. And if you go to the next slide, what you'll see is the final cleaned up version of this terrain data set. This is a culmination of actually over a decade of work trying to get this kind of smoothed out image of the Earth's surface. And indeed, it was these early smoothed versions of SRTM that were what enabled us to build the early versions of our flood models. Next slide, please. And they were in and of themselves huge advances, but actually we've gone a lot further since then. So the data set I've just shown you previously is something called Merit DEM. And this is a data set that we built in collaboration with the University of Tokyo. And what you can see here is some flood simulations being run over both Merit DEM on the left, and then Fathom's latest prior to FathomDEM terrain data set called FABDEM, and that's Forest and Buildings Removed DEM. And on the right, you have something called LiDAR. And apologies if you know what this is, but I'll just illuminate this for those of you who may not be familiar with the term. So LiDAR is effectively a phrase for laser altimetry data. And for the sake of our models, we can kind of call it truth. It's as accurate as we can get with regards to building a terrain data set. So our aim here is to build a model that looks as close to LiDAR as possible. And I kind of crudely summarized FABDEM as being a halfway house between where we were with Merit DEM and where we want to be with a gold standard flood model. So we want to have terrain data sets that look like LiDAR and provide us with LiDAR comparable models anywhere in the world. In many ways, that's the kind of the thing that we've been aiming to achieve since forming Fathom. It's the kind of holy grail, really, of global flood modeling. I'm kind of alluding to it slightly, but we have some good news with regards to these global terrain data sets. And with that, I'll hand over to Chris to talk about FathomDEM in more detail, and I'll be back at the end. So Chris, over to you.
Thanks a lot, Andy. Hopefully you guys can hear me all right. So I'm going to take over and go into a bit more detail about the kind of DEMs which we have available. So DEM, like Andy said, is a digital elevation model. So this represents our best understanding of where the ground is, essentially. And they come in kind of two different flavors. So as Andy mentioned, with Merit DEM and also one called Copernicus DEM, which I'll talk about in a second, these are at the global scale. So we have a value for every 30 by 30 meter grid across the entire globe. There are also local DEMs, and these tend to be LiDAR based. And these are much finer resolutions, so less than 1 meter. But these are only in small locations where detailed surveys have been performed. So we don't have this for the entire globe. Now, these DEMs will essentially give a value above some datum point, and that datum point is normally sea level. So they're very crucial, not just for the geoscience modeling we do here, like flood modeling, but also landslide modeling, infrastructure planning, remote surveys, all these kind of things. Even Google Maps uses them. So, you know, when you're saying, how do I get from A to B on my bike? It's not going to send you up a massive hill. It's going to use a DEM to say, I'm going to route that person around that hill. So they're really ubiquitous. And this kind of difference in scale is something that we need to pay attention to. And we're trying to work out how to go from these global data sets to finer representations. So what's the problem we're really trying to solve? And Andy already alluded to it. Essentially, we're trying to find where the ground is everywhere. So we have these satellite-derived terrain data like Copernicus DEM at this lower 30-meter resolution, rather 30-meter resolution. Now, Copernicus DEM is captured from satellite data, and they fire down a signal, and it bounces back off of whatever it finds on the ground, which means we get a representation of everything that the radar hits. So that doesn't just include the bare earth, that also includes vegetation, buildings, and other objects. And so actually what we've created is a surface model. We haven't got the terrain, we've got the actual surface of everything that is on Earth. Now, as already mentioned, we want to work out how to go from this surface model, which includes the vegetation, the buildings, to subtract away those buildings and vegetation, and hopefully reveal just the underlying terrain. So this is what we call a digital terrain model. And we aim to do this using machine learning. So the previous work, FABDEM, was released in 2022. It was the best in its class at the time. This model essentially took in lots of different data. So this would be forest height, the original digital surface model, Copernicus DEM, world settlement footprint, and many other predictors. And it tried to do two tasks. It tried to say in every single place in the world, what is the potential height, if there is one, of some forest? And if there is a building, what is the potential height of that building? And simply you would say, I would try and guess the heights of the forest, try and guess the heights of the buildings, subtract them away, and do some post-processing. And hopefully that will leave me with just the height of the bare earth. So this is a process of going from my digital surface model to my digital terrain model. And this worked really, really well. We use these models called random forests, and these random forest models worked at a point-by-point basis to do this correction, and you end up with a DEM, FABDEM in our case, which is a best guess at the digital terrain model, so the underlying terrain. But we know we can do better than that. And we know there are some things that this model isn't able to leverage. And that's why I'm going to go on a little aside and talk to you about something called computer vision. So I'm sure lots of people have already heard about this, but in its simplest form, computer vision is essentially the process of enabling computers to reason over images or visual information. And that visual information is essentially 2D information, right? So when deep learning started to really pick up steam in kind of the mid-2010s, computer vision was one of the most impressive ways in which it really improved performance. So using deep learning neural networks, you're able to help these computer vision processes massively increase their performance. So for example, on the top right, I've got an example here of identifying objects on a street. So this would be used in like a self-driving car. And the computer vision approach is able to look at the entire scene and reason over what the content is and see that there are vehicles, pedestrians, street signs, and obviously then do something with it. And there's, for example, other examples in geospatial analysis. There's a example here on the bottom left of a model which is able to classify different areas in terms of buildings, vegetation, water, and roads. You can see how that would be very useful for many different tasks. And of course, Facebook do some funny things with detecting people and their poses. But computer vision is really ubiquitous. I mean, if you have a mobile phone, like we all do, it uses computer vision in many, many different ways, from the fact that you can now search on your phone for pictures of a dog and it will show you all of the pictures which contain dogs. That's using a computer vision model to do that task. And even to unlock your phone, it scans your face and can tell whether or not it's actually Chris logging into the phone or someone trying to steal his credit card information. So very, very ubiquitous and hugely improving the performance since deep learning really came of age, I guess. So to understand the impact of computer vision, let's try and I want to do a kind of interactive test with everyone. And we're going to play a game. So we're going to play the classic game, is it a horse or is it a zebra? So challenge is, I'm going to show you an image and you're going to look at that image and tell me, is it, for example, on the left, a horse, or is it on the right, a zebra? Okay. Now we know that when we solve this problem, we can just look at the image and we have this nice understanding. We can see the full context. We can see that it's a kind of horse-shaped animal. Has it got stripes? We do all these kind of reasoning processes and we're able to look across the entire image and make sense of it. But what we're going to do is a bit of a twist on it. Instead of looking at the entire image, I'm going to show you just one small component of it. And we're going to see if you can do the task. So maybe fire up the chat. Grab your keyboards and I'm going to show you the first one and I want to see some, I'm going to try and open the chat box here to see if we can get some accurate guesses. Okay, so first one coming up. Is this a horse or a zebra? See who's awake. Maybe you can answer that. We've got a couple of zebras. Cool. So this is a good example. Thanks very much for the interaction. This is a good example where we've kind of gotten lucky, right? We've managed to find a location in the image which actually contains a lot of relevant information for solving this task of, is it a horse or a zebra? So now, as you can probably guess, correct, right? We've got a zebra. Then let's try another one. Is that a horse or a zebra? Bit of a tougher one here. Here we've got a horse. Horse. Right, let's have a look. Is in fact a horse. So again, a bit more of a challenge, but because we're not able to look across the entire image, we're focusing on just one small point, the task becomes significantly harder. So one more. Okay, it is. This one's a zebra. And finally, one last one. Any last guesses? Horse or zebra? Brilliant. It's actually a horse. Well guessed, guys. Hopefully some people got 4 out of 4. So what's the point I'm trying to make here with this ridiculous game? Well, if we asked a computer to do this task, we know that we can represent this data in some special way. And the way we represent that is as pixels. Okay, now these are obviously a bit bigger than the pixels in the image, but go with me. Each pixel contains some information, and when we consider them all together as a whole in a grid, they come together as greater than the sum of their parts, and we're able to make much more sense of what is actually happening in this image. But the point I'm trying to make here is that without computer vision, we're simply looking at one part of the image at a time, and that task becomes a lot harder. And that is actually very similar to what FaBDEM was doing. So there's a bit of subtlety to this, but as a whole, FaBDEM was looking at one location at a time, considering all the information at that one location, and then making a prediction for that one location. So we said, well, what if we can empower FaBDEM with computer vision to take advantage of the fact that we have all of this information in related pixels and use that to help solve our problem? So computer vision for digital elevation models, the task is, as Andy said, to go from this FathomDEM, the digital surface model, which we can see contains all of this kind of noise and structure, which we don't want because we know that's not the actual terrain, and take it over to translate it into something much more akin to LiDAR. And if we can enable our model to use computer vision and really consider the context of the 2D image we're seeing in front of us, hopefully we can produce something quite powerful and good at solving this task. And that's exactly what we did with FathomDEM. So FathomDEM is an improved global terrain map, which uses a clever deep learning technique called a vision transform model. But essentially what we're doing is we're taking the similar approach as with FaBDEM, but enabling it to consider this 2D context and reason about it and make predictions about it. So for the gory details, and for those that are actually interested in this kind of stuff, this is what we call a pixel-wise regression. And what that really means is we have some neural network architecture, which is a UNet, which I'm showing at the top here, and we feed in 2D images of all of these different predictors, and they're all in the paper, and we can elaborate on it if you like. But one of these is FaBDEM. So FaBDEM plus a bunch of other reasonable information that we think is helpful for solving this task gets iteratively processed down through the UNet and then back up again to make a 2D prediction. So not only are we feeding in 2D images and allowing our model to reason over that image, much like we did with the entire image of the horse or the zebra, we're actually asking it to predict in 2D as well, to hopefully get some kind of semblance of structure and consistency across our predictions. And this is something which FaBDEM wasn't able to do. So this is the new approach. This uses a cool technique called a vision transformer. And some of you are probably aware of transformer networks, the transformer architecture. It's incredibly powerful and it's kind of swallowing up all of machine learning at the moment. And ChatGPT, for example, uses a transformer approach. And what we do with vision transformers is we look at images and patches within images and different parts of the image in the same way that ChatGPT is able to look at words and sentences and really work out what's happening across the entire image rather than just in small locations. So this is really empowering the model to take in all that contextual information, which is useful for working out how to go from the digital surface model to the trained model. So one of the issues when training these models is they're quite data hungry. And so we had to pull together as much data as we could to solve this problem. And we need examples, right? We need examples of FaBDEM and examples of LiDAR, so the source and the target. And we want to train our model to say, go from this to this. So the yellow dots show us, or the yellow and gray dots show us where we have this, the LiDAR data. And of course, we have FaBDEM data for everywhere. So our game is here, let's learn in the places where we do have LiDAR and teach a model to go from one to the other by showing it both, and then apply it to the rest of the world just by using the fact that we now have FathomDEM to convert FaBDEM to something which should look like LiDAR. So how well does it work? Well, I'm going to show you two examples here. So we have Alabama in the USA. So it's a coastal region, and you can see there are all these kind of river channels, and Nouvelle-Aquitaine in France, where we have, again, a river channel, which is obviously quite relevant to Fathom, and quite a flat region around it. So these are typically really challenging areas for us when we're building up these kind of global DEMs. And as you can see in CopDEM on the far right-hand side, there's a lot of unwanted structure. So we know that the LiDAR tells us that these planes should be relatively smooth, but in CopDEM, there's a lot of noise. And this comes from buildings and from crops and forests and all these things which the digital surface model captures that we don't want. So when we applied FABDEM to this, the first version of our model, it does a great job at removing quite a lot of this noise. So there's still some that remains, but it's really doing quite an impressive task to clear up this data and make a much more usable DEM. But now if we add in the computer vision approach, which is FathomDEM, we can see that we're really starting to approach something which is significantly much more like LiDAR. So we're really closing that gap between the original digital surface model and what we believe is the best terrain model we can make. So statistically, if we take all of the data that we're validating on, we're testing on, and look at all the pixels and calculate the mean error across the entire data set, we can see, like, we have these three statistics. We have mean error, mean absolute error, and RMSE. The original data set CopDEM, so this is compared to LiDAR as a ground truth. How incorrect is it with respect to what we believe is the digital terrain model? And you can see there's this really broad distribution. So there's lots of high errors. When we go to FABDEM, things tighten up significantly, but then FathomDEM really takes it into a league of its own, where we suddenly have this really nice sharper peak and improves significantly on the previous approaches. Now, one really nice thing, I showed you that distribution of where our training data was. We trained one single model to work for the entirety of the world. We haven't specialized this model in certain locations because we wanted one thing which could do everything. And so we've showed it a variety of different environments to hopefully make sure that it's able to make its correction for a variety of different environments. And this is in contrast to other DEMs, for example, Diluvian DEM and Delta DTM, which were designed specifically for coastal regions. Our approach, when we compare it to these DEMs, actually improves performance in these coastal regions. So again, we've created one generic model which should work for everywhere, and actually it's outperforming targeted specific coastal DEMs in those coastal regions, which we were very, very pleased with. So that's all great that we can reduce the error and we have something which looks a lot more like a digital terrain model. But really what we care about at Fathom is, can we use it to create a good flood map and use our, basically simulate a flood onto that terrain and see what it looks like and hopefully get something useful. So on the right-hand side here, I'm showing you the flood map that we created using LiDAR. So again, the ground truth, our best bet of what we believe the digital terrain model is. And we simulate our flood and we have this structure. Now, there are two different regions I want you to focus on. We have this kind of top region here where we can see quite a lot of detail and quite a big flood extent. And then this branching feature here in the circle on the bottom. When we perform this flooding simulation using FABDEM's DEM, or the FABDEM DEM, you can see that we're completely missing this channel. So FABDEM has made some correction to the original digital surface model, which has somehow blocked this channel from opening up. And similarly, at the top, there's nowhere near the same level of flooding that we see in the original LiDAR. So there's some work to be done here with FABDEM. If we do the same performance, same simulation again with FathomDEM, we now recover a lot of this structure. And this is really great to see. We suddenly have this channeling opening up at the bottom in the circle and much, much better definition in the top. So this is really promising and telling us that we're now closing that gap between where LiDAR is and where global DEMs can now be thanks to FathomDEM. So another quick example here, I've got the LiDAR on the far right, and this is actually the FEMA flood zone, which is used in the US. And FABDEM, again, has some kind of unwanted flood extent, as you can see it on the left in the middle. And when we go to FathomDEM, this improves significantly, and we start to really approach what the performance we see with LiDAR. But to put this into some numbers, we can use the standard measure of flood map performance, which is the critical success index. And this is really telling us on a scale of 0 to 1 how similar to the actual flood was our simulation. So 1 is a perfect score, but it's unrealistic to get that. So 0.75 to 8 is considered a really strong score. And I've included 3 different floods. So we have one from Iowa, one from FEMA, and the Environment Agency, the different flood sources. And we've compared our 3 simulations. So the interesting thing to note here is where we have improved upon FABDEM, we have now pretty much approached the quality of a flood map created with LiDAR. So according to this critical success index, which is much better than just kind of looking at it by eye, we've now essentially removed the error due to the terrain model that we're using, thanks to this FathomDEM DEM. So we're really happy with this performance. So at that point, I think I'm going to pass back over to Andy, and I'll be here for any questions at the end.
Thanks, Chris. I'm genuinely sat here smiling when I listen to all this work, because it's really amazing the progress that's been made. Admittedly, over quite a long period of time, but I think there's been a real acceleration in our ability to build these kinds of terrain data sets, principally, frankly, since we've been getting a handle on machine learning techniques, and Chris has played a huge part in enabling us to leverage those tools as much as we can. So huge thank you to Chris. And Chris mentioned, like, what we really care about here at Fathom is building flood models. That is kind of true. It's how we deploy the data, but actually there are any number of different ways in which to use terrain models. This sounds like I'm being a bit hyperbole here, but there's something fundamental in humans, right, around mapping and understanding what the Earth actually looks like. Like, what does the Earth's surface actually look like? This is what we're talking about here, is data sets that enable us to do that for the whole planet. And unsurprisingly, there are any number of ways in which you can use these data outside of flood models. You can use them for geological surveys and modeling. Even things like biology can utilize these data sets, all the way down to gaming. And one of the obscure ways in which we've seen our terrain models used has been in virtual reality. So if you were to buy some real estate in Earth 2, the Earth in there, the shape of the Earth's surface is actually based on terrain data sets built here at Fathom. So really, the range in which you can use these kinds of data is very large and frankly growing all the time. Next slide, please. So I want to summarize quickly what we've heard so far, and I guess I'll start with the fact that machine learning is really transforming the ways in which we can undertake terrain data processing. I think back to the early days of us trying to do this, and I showed you those images in the Mekong Delta in Southeast Asia. And lots of our work then was really kind of rudimentary, low-pass filter style work, where you pass a window over a terrain data set and just pick out the low points. It seems incredibly blunt, frankly, and unintelligent compared to the work we've just heard about. And that's all down to really the fact that machine learning is, frankly, ideal for this kinds of work. And hopefully, as you've seen, we can deploy it in some quite amazing ways. And that application is really yielding the next step forward in global flood modeling capabilities. We can use this to build LiDAR kind of skill level models anywhere in the world. And that's the last point here that I want to make, is that, and this, people might argue with me on this one, even here at Fathom, but I think what we've seen is that the modeling gap, at least between local and global terrain data sets, has been closed. I mean, there was a gulf between our global models and our local models 10 years ago. That's really no longer the case. There isn't a gulf. And actually, the terrain data aspect here is, as we've seen with those CSI scores, has been largely closed. So that in and of itself, I think, is an amazing feat and something that's really, really exciting. And next slide, please. And with that, we come to the end. You can read the research paper. It's available via that link. It will be released as a product as well later this year. But for now, there is also a poll that's been put on your screen. Hopefully you can see it. Please do interact with it as well if you can. We want to know your interest in these data. Why are you interested in finding out more about it? And of course, if you'd like to have a demo of some kind, then let us know and we'll get in touch and we can show you what these data look like. And do we have any questions in the Q&A? Let me have a look. If you do have any questions, feel free to post them in the chat and we'll get to them. We have one here. Oh, can I access the products already? You can for research purposes. So they are available via a Zenodo link right now, but not commercially. So it will be released as a product to be used by anyone later this year. But for now, for research purposes, the data are available. You should be able to find them via the research paper. So yeah, go to that link and get a hold of the data. We have another question. Is this the only way in which AI is being used at Fathom? The answer there is no. We are using similar techniques elsewhere in the models. One thing I always emphasize is that Fathom builds models that simulate physics fundamentally at their heart. So we're building physically based models, things that solve algorithms that describe physical processes effectively. So very much not machine learning at their heart, and there's good reason for that. But in terms of how we construct the models, then yes, we are using machine learning to help us build the various input data sets, principally things like defining extreme river flows, defining extreme rainfall. Machine learning is proving actually a perfect fit for that kind of application. This might be one for Chris. Can you say something about the size of the compute and storage infrastructure needed for running a model globally to generate this product?
Yeah, of course. So actually, we managed to train this model with quite a modest in-house setup. So the data itself is probably the largest part, and it's a few terabytes of those predictor data sets. But the model itself isn't particularly big, especially by kind of today's standards of the chat GPTs of the world. It's a tiny fraction of that. There's more details in the paper, but yeah, even on a kind of commodity off the shelf GPU, we managed to train this in like half a day or something. So it's not huge. Yeah.
Thanks, Chris. Maybe another one for you. What datum is used globally? Do you remember?
I think it's local sea level, although I'd probably want to defer that question to one of our geospatial experts. But yeah, I'm pretty sure it was sea level because we used LiDAR and FathomDEM. Yeah.
I think the vertical datum, if it's similar to the flood models, will be WGS84 from memory. But yeah, that'll for sure be in the research paper as well. Okay, well, if there are no more questions, we will finish early, so you're getting back 10 minutes. I'll say again a big thank you for joining us. Really appreciate it. If you have any questions, do reach out and we'll get back to you. And yeah, please join us again at one of our events and have a good day, evening, wherever you are in the world. Thanks.